It's okay. Good.
Good afternoon. My name is Mercy Budu from MIT University, and my presentation this afternoon is entitled Performance Evaluation of Soft Seas Created by Hydrogen, where the abbreviation soft C stands for solid oxide crystal. Now, getting into a little bit of a background of what they are, these are simply electrochemical conversion machines that convert chemical energy in the form of fuels like hydrogen, syngas, biogas into electrical energy with little carbon emissions. Now, the basic working principles of these machines is that you have oxidation of your fuel occurring on your anode side, and you have reduction of your oxygen occurring at your cathode side. So at your cathode, your oxygen atoms become ions that then can travel through our electrolyte to react with our fuel on the anode side to produce electricity. And one distinguishing factor with solid oxide fuel cells is that they operate at relatively high temperatures of between 600 and 1000 degrees C. And this contributes to what I like to call fuel flexibility. And we'll get into that in the next slide. So, what is fuel flexibility? We have a wide range of fuels that can be fed into our solid oxide fuel cells, which is a little contrary to what we know with pen cells, where we have to have pure hydrogen. But in this case, you can put hydrogen with some impurities and still generate electricity. And this is mainly due to a few of the characteristics of our solid oxide fuel cell. Number one is our internal reforming action. Because they operate at high temperatures, you do have reforming of your hydrocarbon-based fuels that occurs right in the anode of your solid oxide fuel cell. So reforming is breaking down of long hydrocarbon chains into small ones. So by the presence of our nickel catalyst and the high temperatures, these chains are able to be broken down into small ones and then reacted in order to generate electricity. Due to these high temperatures that they operate at, they're really beneficial in using in cogeneration systems where you can leverage the excess heat that comes off of it into another system, and they exhibit desirable efficiency. Let's look at the next slide over here. This is a comparison of fuel cells and conventional power generation methods. At the bottom here in blue, we see what we normally use to generate power. You have your gas turbines, steam turbines, amongst many others. And at the top here in your yellow and green, you have your fuel cells, with your solid oxide fuel cells showing the best electrical efficiencies amongst our fuel cells. And they perform even better when they are coupled with other power generation systems such as gas turbines. Okay. Now, even though we've talked about how beneficial these are, they still come with huge challenges. The biggest challenge is degradation. So over time, you see a significant gradual loss in the performance of your solid oxide fuel cell. If you look at the graph on the right here, this is a graph of current density and operating time. And we can see that as we keep operating our solid oxide fuel cell, gradually we get less current per square centimeter of minute. Now, this is largely attributed to the presence of impurities in our fuels and also the high temperatures at which they were at. So some examples of degradation that happens in solid oxide fuel cells is nickel coarsening. You have carbon deposition on your anode. You can also get mechanical failure and sulfur poisoning. Now, the first image here shows nickel coarsening in a nickel slash atria stabilized zirconia solid oxide fuel cell. A shows the original state of our anode, and as we operated through, you see that these nickel grains become rounder and bigger, and that leads to the coarsening of our anode. The second image here is a representation of sulfur poisoning. So the sulfur in your fuel reacts with hydrogen to make hydrogen sulfide, and these attach onto the anode of your solid oxide fuel cell. These two images here are before and after pictures of a solid oxide fuel cell operated with methane, which contains carbon. So the first image is an image before operation, and the fourth one is after some hours of operation. So these dark spots over here are where carbon are deposited on your anode. And the last one here is mechanical failure, which is crack propagation and growth in your anode / your electrolyte. So the first image, there is no crack, but eventually when you get to the third one, you see a crack forming, and then eventually this crack begins to grow because of the constant redox cycling that happens in a solid oxide fuel cell. Now, where does steam play into this whole scenario? Various literature has shown that the presence of steam in your fuel actually helps prevent with carbon deposition. So steam reacts with carbon to form carbon dioxide, carbon monoxide, and hydrogen. So instead of attaching to your anode, you get those products instead. Another thing is that there has been well-established research in chem cells on how the presence of water affects our fuel cell, but not much has been done in solid oxide fuel cells. And that is where we come in. What exactly is our motivation? From this graph, we see that the hydrogen market is anticipated to grow, but most of our hydrogen coming from steam methane reforming and also coal gasification. But we have the little bar here, which is others. And in this little bar, we have what we call metal water reactions, where from your basic chemistry, you add water to a metal and then you get hydrogen. However, it's not that simple because you need to determine reactivity and how much you get from it. So various research has been done, and it has been proven that you can generate hydrogen from aluminum water reactions, but it has to be done under supercritical conditions. And this is where I come in, because that is what my research group does. So we want to know how would the system pair well with a solid oxide fuel cells, noting that the hydrogen from these reactions contains steam. So do we just feed it directly into the system, or is there a need to condition this hydrogen before it is utilized? So performance evaluation in this context has been classified into 4 distinct aspects. We have electrochemical efficiency, electrical efficiency, thermal efficiency, and fuel utilization. And what we're doing is basically mixing steam and pure hydrogen of different compositions and feeding it into our fuel cell and performing some tests. This is a PNID of our experimental setup. I'd just like to divert your attention to 3 key machines here. So we have our solid oxide fuel cell over here, we have our steam generator over here, and these 2 modules are part of our control unit. So what we do is we supply hydrogen to our control unit, where we are able to alter the flow rates of it, and then we supply steam from a separate line and mix those 2 before putting them into our solid oxide fuel cell. For context, the solid oxide fuel cell that we're using is a whole stack that consists of 30 cells, which is very unusual in the research space. However, this was made specifically for research purposes. It has an active area of 61.5 centimeters squared and can go up until 750 watts with a maximum voltage of 32 voltage DC and 40 amps. We also have a steam generator that can go up to 200 degrees C, and we're able to alter the operation of our steam generator based on our flow, the desired pressure, not the desired temperature. And this is our data acquisition / control unit. So this unit has a variety of different machines. We have a computer for data acquisition, we have a gas mixer, mass flow controllers as well. And we also have a load bank that we use in order to perform our IV experiments. So from this, what we do is we conduct our experiments, And we take these four key measurements, and then we produce our polarization curves and also determine the efficiencies. This is a work in progress, so we still haven't gotten that far. However, we'll show the preliminary results. So this is an ideal polarization curve for a solid oxide fuel cell, where you see two key points of reflection where the graph changes, and these key points indicate where you have different losses occurring. The image on the right is experimental data from another set that uses pure hydrogen as well. And this is our data. So following our data, we produce a maximum of 28 volts under these conditions that we specified, and we also see those same regions in our data where we have your activation region, you have your atomic region, and you have your concentration region. And from this is our base case that we'll use for comparison for future cases where we add in our steam. So from this, we have gotten our baseline, and in future, what we will do is add in steam to these compositions and then study what happens afterwards. Any questions?
What's your expectation on your final results?
Our expectation is that gradually you'll see this blue line over. You see this blue line over here begin to start down here, and down there. So what we want to know is exactly how much steam produces how much loss in your voltage, so that we are able to use this data in future for modeling simulating purposes as well, because this is not currently available.
What do you expect for the degradation? How do you sort of calculate and evaluate?
Yes, so now we're focusing on just the efficiency, but in the future we will be doing these experiments over a longer period of time.
Any other questions? Okay, let's handle some of that. So, well, I feel a little bit ahead of time, so I don't know whether the conference wants to keep the time or the discussion. There's one more? Yeah, one more. I think we should go ahead. Yeah. The last one is from Sean Warnock, and the topic is hydrogen production coupled with